Welcome to Module C. In this lesson, we're going to be looking at more complex multi-process systems. We're going to be adding the concepts of recycle and bypass. So, recycle and bypass are very common. Basically, what happens is you have a process or a portion of a process, and you have a stream that either splits off before it enters the process and goes around, that would be a bypass, or it goes through the process, but a portion of it is sent back to go through the process again, that would be a recycle stream. Recycle streams are very common. They're going to be used to recover, say, an expensive catalyst that isn't used up in the process, but is necessary for the process to work. Or sometimes we'll use it to dilute a process stream. We also can use these for control of process variables, or just simply to keep a working fluid circulating so that we always have adequate flow rates. Bypass streams are going to be most commonly used for control. In order to analyze these, the easiest thing to do is to draw a little box around the mix point or the split point where everything is going crazy on our lines. Just draw a box around it. And that way it just looks like a little process, in the case of a split point, with a stream going in and two streams going out. Now, split points are a little bit more interesting than most. First of all, the material balance, they're going to be steady state. So what goes in is equal to the sum of what comes out. But what's really interesting and makes these special is that the composition is going to be the same in all the streams. If you can remember this little fact right here, then it's going to help you with solving many problems much more efficiently. Now, mixing points, again, just draw a little box over it. In this case, we have one stream in, another stream in, one stream out. So N1 and N2 is going to equal in the stream that goes out. Now, the compositions here will probably be different, right? If you were to mix up two different batches of anything, whether it's lemonade or maybe you're making lemonade and iced tea. So the compositions are different in the two things, and what you come out with is a lemonade sweetened tea. Okay? So analysis is not very tricky. The only thing that you really need to learn that's new is that at a split point, the composition will be the same in all streams. So let's look at an example. Now in this example, we have feed coming into Unit 1. We have Unit 1 somehow separates out material A, and the rest of the A and the remaining B come out in this exiting stream M1. We have then some new feed that's mixed in that contains C, a third component. Now that means that after the mix point we have something that contains the remaining A and B from Unit 1 as well as C, so now we have three components. This goes into Unit 2 where you obtain two different mixtures of different compositional makeup. And those are shown right here. One is going to be 475 grams per second. The other one, I don't know how much there is, but I know its composition. So based on this, can we solve for the unknowns? And in particular, can we figure out what the composition is of our products? So in this particular case, the basis is given. So we'll just do this all based on 800 grams per second fed to Unit 1. And then I want to figure out my materials table. This one is not too hard because everything was basically well described in the diagram. So the flow streams were not named directly, so I've named them Feed 1, Unit 1 product, Stream 1, Feed 2, this is the mixture, and then unit 2, product 1, unit 2, product 2. So based on those, in feed 1, I have a mixture that's 0.2 mass fraction A, 0.8 mass fraction B, and no C. This flows at 800 grams per second. Unit 1 product is going to contain only A, flowing at a rate of 100 grams per second. So 100% A, no B, no C. Stream 1 contains some A and it contains some B. Let me erase that. But it does not contain any C. The flow rate of this is unknown. We'll name it M1. Feed 2 contains only C at the rate of 200 grams per second. So no A, no B, pure C, and the flow rate is 200 grams per second. The mixture, well, I don't really know much about it except for X2, Y2, and Z2 were the designated compositions, and the flow rate is M2. For Unit 2's products, 1, I know the flow rate, but not the composition. And for the other, I know the composition, but not the flow rate. So the material table is not any more complicated than it was before. So let's look. Okay, so now let's look at the degree of freedom table. So for the degrees of freedom, what I do is I set this up for each of my units. So I have Unit 1 and Unit 2. Those seem very clear and obvious. But I also have the mixing point. So that will be treated like a process unit. And then, of course, whenever I have a complex system, I always want to consider the overall system also. Now, my streams for Unit 1, I have feed 1, Unit 1 product, and stream 1 that come in and out of this. So feed 1, Unit 1 product, and stream 1 are what go in and out. The variables associated with these are simply X1, Y1, and M1. Okay. So, how many material balances can I write on Unit 1? Well, I have A and B. I have 3 listed in the table, but for Unit 1, this is uniformly 0, so therefore I really only have 2 material balances I can write. For sum of x's, I have one that has the x's in it, so I have one of those. I have no process specs, and to calculate my degrees of freedom, take the number of variables minus material balances and sum of x's and specs, and I end up with 0 degrees of freedom. So this one is good to go. I could get started solving this one right away. But let's go ahead and look at the other units. So let's look at Unit 2. That's the next one that we feel like we understand, correct? So this one is going to be the mixture coming in, okay, this stream. Well, that's a little hard to read. Okay, the mixture coming in, and then the 2 products come out. In those, I have 1, 2, 3, 4, 5, 6, 7, 8 variables. I'm not going to list those. Now, how many material balances can I write this time? Well, I have all 3 components involved in Unit 2, so I can write 3. Sum of x's, I have one for this stream and I have one for this stream, so I can write 2. I have no process specs, but 8 minus 3 minus 2, oh wow, that leaves me with 3 degrees of freedom. Not really anxious to tackle that one, right? So let's look at the mixing point next. If I treat this as if it's just a little process, okay, I have the C feed, so feed 2 coming in, I have stream 1 coming in, and the mixture coming out. So feed 2 and stream 1 go in and the mixture comes out. So that is this one, and this one. I have therefore 1, 2, 3, 4, 5, 6, 7 variables. Now this does involve all 3 components, so I have 3 material balances. I have 2 sum of x equations, no process specs. 7 minus 5, however, is 2, and so I have 2 degrees of freedom. So this one is not quite ready to solve. What about that overall balance, however? So the overall balance is when I block off all of this, and I have my feed 1 and feed 2 come in, and then what leaves is product 1 and unit 2's product 1 and 2. So I have 5 streams involved here. So feed 1 and feed 2 come in, and unit 1 product, unit 2 product, and unit 2 product 2 come out. So variables, well, this doesn't have all that many unknowns, right? So I have 1, 2, 3, 4 unknowns. Okay. I have 3 materials, A, B, and C are all involved. I have 1 sum of x equations, no process specs. The degrees of freedom are 0 here. So the overall and unit 1 are both well specified. I can work on those directly. And my thought process is, therefore, to do this, well, overall or unit 1, it doesn't matter. I can do those in either order. And then next, it looks like probably the mix point will be the next easiest, and then unit 2. So I'm going to analyze these in sort of this order prioritization. So let's now start writing the material balances. Okay, oh, there it is all filled out. So for the overall system, I can write a total mass balance, a balance, a B balance, and a C balance. Now remember, these are going to be redundant. But my total mass, I have 800 coming in and 200 coming in the feed 1 and feed 2. And coming out, I have 100 from unit 1. I have 475 from the product of unit 2. And then I have m dot 3. Now this one I can very directly solve for, and m dot 3 therefore is 425 kilograms. Grams per second. Okay. So what if we look at some of these other balances? Well, 0.2 times 800 is how much A came in. In stream 2, 0A came in. And the A that leaves, well, all of product 1 plus X4 times 475 plus 0.012 times M3. Now I know M3 at this point, so I can solve for X4. Okay, and doing that, I find that X4 is 0.1. Okay. Now I can do B. Okay. B also contains 0.8 times 800. Nothing came in feed 2. Nothing goes out in unit 1 product. And I have compositions here, and I can solve for Y4. Y4 is 0.82126. Now I also have C, okay, and the C balance tells me nothing came in feed 1, 200 comes in with feed 2, nothing leaves in product 1, and Z4 times 475 plus 0.4 times M dot 3. And again, I can use this with Z4 to find Z4, and that is 0.06316 grams of C per gram. I'm going to check these using the sum of x's, that x4 plus y4 plus z4 equals 1, and they do. Okay, so using the overall system, I've been able to solve for 4 of my unknowns. So let's go on to Unit 1. That was the other one I said was a good starting point. So Unit 1 says that 800 grams per second enter, 100 plus M1 exit. Again, I can solve this directly for M dot 1. And then I can do balances on each of the components. For A, I get this little balance. I can, because I know M1, I can solve that for X1. For B, I have 800 times 0.8 equals 0 plus Y1 M1. And of course, that tells me that Y1 is 0.91429 grams of B per gram, and those units were wrong, grams of A per gram. And there is no C balance. My additional equation is the sum of x's, which simply says that x1 plus y1 needs to equal 1, and they do. Okay, what happens now if we move to these other ones? The other ones did not have a degree of freedom of 0, but I already know some of the information. So let's look at those. Let's look at the mixing point. Okay, so for the mixing point, I have M dot 1 plus 200 enters, and M dot 2 leaves. Now this would not be an easy equation to solve except for the fact that I already know M dot 1, right? I just found that M dot 1 is 700. So therefore, m dot 2 is 900 grams per second. Okay, what about an A balance? Well, I have x1 m dot 1 plus nothing that came in with stream feed 2 is going to be x2 m dot 2. I know x1, I know m1 dot, I know m2 dot, so therefore I can solve for x2, and x2 is equal to 0.06667 grams of A per gram. I can do a similar thing for B. And for C, I can, well, nothing comes in with the product from unit 1. 200 comes in with feed 2, and this is going to be Z2 m dot 2. And based on that, Z2 is going to be and again, my additional equation, sum of x is equal to 1, and indeed they do. So at this point, I know all the various variables that I would need. I'm ready to simply answer the question. I can also do unit 2. Unit 2 very quickly. M dot 2 equals 475 plus m dot 3. I know all of those, so this just simply allows me to check. x2 m dot 2 equals x4 times 475 plus 0.012 times m dot 3. And again, this all just allows me to check. And I could go through and do all of those if I wished, but they're all just simply going to check. It's a good thing to do, though, where you check your work. And so if I answer this, and unit 2 product 1 flows at 425 grams per second, and product 2 contains 0.116 grams of A per gram, 0.822 grams of B per gram, and 0.063 grams of C per gram. And so we have fully solved this equation. In the next video, we're going to come back and look at another example, just so that we can see different ways that these are all put together.